Here's a weird one for you. Have you ever stopped to think about why you can bend a paper clip into, well, any shape you want, but a diamond, the hardest stuff on Earth, will literally shatter if you hit it just right? It feels totally backward, doesn't it? Well, today we're going to solve this little mystery, and believe me, the answer is hiding in a place you would never, ever expect.
So this is the puzzle, right here. On one hand, you've got a simple metal paperclip that just gives, it bends. And on the other, you have a glass cup that just breaks, poof. They're like complete opposites in how they handle force. The secret to why this happens, though, it isn't something you can see. Nope, for this, we have to go much, much smaller.
All right, to get to the bottom of this, we need to kind of shrink ourselves down. I'm talking way, way down, millions of times smaller than a single grain of sand, because the real clue is hidden deep down inside the very structure of these materials.
That's right. The entire reason for all of this comes down to how their atoms are arranged. It's all happening at the atomic level. So let's zoom in and uncover the first piece of our puzzle, shall we?
Now, you might picture the atoms inside a piece of metal being all perfectly arranged, right? Kind of like a perfect stack of oranges at the grocery store. And, for the most part, you'd be right. But here's the thing, they're not perfect. They have these tiny little flaws.
And this is our first major clue. You see that one row of atoms that's kind of misaligned? That's an imperfection, we call it dislocation. A really good way to think about it is like a tiny wrinkle in a perfectly made bed. And for a metal to bend, these little wrinkles have to be able to move.
So here's the key takeaway. Bending is really just what we see on the outside, when billions of these tiny atomic wrinkles are sliding through the material on the inside. If those wrinkles can move easily, the material bends. If they're stuck and can't move, it breaks. Simple as that.
Okay, so that leads to the next logical question, right? If these wrinkles are the key, what's stopping them from just sliding around all the time? What's holding them in place?
Well, the answer is this kind of internal friction. It's got a super technical name, Peierls-Nabarro stress. But don't worry about the crazy formula here. Just think of it like this. It's the minimum amount of push needed to get that atomic wrinkle to start moving. The lower this friction is, the easier it is for the whole thing to bend.
So our mission, if we choose to accept it, is to figure out the secret recipe for the lowest possible internal friction. How do we design a material that just wants to bend? How do we do that?
It's pretty amazing, actually. The secret formula for creating this super low-friction path for these wrinkles to travel on, it all comes down to just two simple distances, at the atomic scale, that is. That's it. Just two little measurements tell us pretty much the whole story. And here they are, our two key players. First, you've got D, which is the space between the rows of atoms. Think of these like lanes on a highway. Second, we have B, the distance between the atoms themselves in those lanes. Think of those as the cars. The friction depends entirely on how wide the lanes are and how tightly the cars are packed together. Okay, let's look at our first piece of evidence. This graph shows the friction, that Peierls stress, on the vertical axis, and the space between the highway lanes, D, on the bottom. Now just look what happens as the lanes get wider, as D increases. The force needed to move that wrinkle just plummets. It falls off a cliff. So rule number one, wider lanes make it way easier for those wrinkles to slide.
And now for clue number two. This graph shows what happens when we change the distance between the cars in the lane, B. And notice this, when the atoms are far apart, meaning a large B, the stress absolutely skyrockets. It goes through the roof. But when they're packed together nice and tight, the path is way smoother and the stress is much lower. So rule number two, you want tightly packed atoms.
So there we have it. The perfect blueprint for a material that bends easily is one that has the widest possible gap between its atomic planes and the most tightly packed atoms along those planes. This combo creates the smoothest, lowest friction possible escape route for those atomic wrinkles.
And honestly, this is the perfect way to picture the whole thing. Imagine you have to move a giant, heavy carpet across a room. Trying to drag the whole thing at once? Yeah, good luck, almost impossible. But if you create a little wrinkle in it and just push that wrinkle across the carpet, it's surprisingly easy. That wrinkle is our dislocation. And having those wide planes and packed atoms, our large D and small b, that's like pushing the wrinkle over a smooth, polished floor instead of trying to do it on rough concrete.
Okay, so we've cracked the code. We've got the theory down pat. Now, let's apply this to the real world and see exactly why something like gold bends and a diamond shatters.
And wow, this table basically tells the whole story. Over on the left, you've got structures like gold, They're called close-packed, which is just a fancy way of saying their atoms are packed super tightly, that's our small b, and their planes are far apart. This gives them a friction rank of 1, the lowest you can get. Then on the other side, you have diamond. Its atoms are all spread out in the super rigid lattice, giving it the highest friction rank possible. Its wrinkles are locked down solid. They can't slide, so the whole thing just shatters.
And that's really the whole shebang in a single sentence. It's not about being strong or weak in the way we normally think about it. It's all about having the right internal setup, the right architecture that gives those atomic wrinkles a nice, smooth path to travel.
So we've solved the mystery of how metals bend. It's all about making that low-friction highway for atomic wrinkles. But that just brings up an even bigger question, doesn't it? How much force from the outside world, pushed at just the right angle, does it actually take to get that slide started in the first place? Well, that's a story for another time. We'll see you then.